Today I'm going to talk about how to optimally plan for time partial order specifications. Increasing efficiency is crucially important in many domains, from manufacturing to administrative processes. These processes are called workflows and are often imposed with precedent and timing constraints. For example, in aircraft turnaround, passenger can only deboard after stair truck is placed, or unloading takes at least 15 minutes. Recently, a new model called Time Partial Order Specification was proposed to model such constraints. Time Partial Order TPO models specifications with nodes representing the events and edges representing the partial orders, and clocks, denoted by C, represent timing constraints. It acts like a stopwatch and can measure local time. Given a TPO, how can we then come up with the optimal plans for robots in this environment? So our problem formulation is the following. Find plans in the environment that minimizes the end time subject to the TPO specifications. Our approach is to abstract the environment to a deterministic transition system, DTS, and associate its states to the events in the TPO. Then, we can formulate it as a generalized traveling salesman problem with time windows and precedent relations. Edge costs represent the traveling time between events and can be obtained via shortest path algorithms on DTS. We solve a mixed integer linear programming problem to find the optimal plan that visits each event once. We can handle duplicate event labels, and this is useful when the same task can be completed at multiple different states. With a very easy modification, we can also extend it to multiple robots. We now show the physical experiment. The task is to complete the aircraft turnaround task with 3 Jackal robots simulating the ground staffs. The robot on the right first brings the conveyor belt next to the aircraft to start unloading and loading, which takes some time, so it will stay by the aircraft. The bottom left robot is in charge of catering vehicle. However, the catering can only be started after the stair track is placed and the boarding is completed, so it will also wait for some time to start and complete the catering service. Let's rewind the video to see the robot on the top left. On top left, the last agent brings the stair truck and immediately heads to the refueling vehicle to start refueling. The refueling can be completed unattended, so the robot lets the other robot to handle moving out the vehicle later. After loading is completed, the bottom right robot moves out the conveyor belt and subsequently heads to the refueling station to move out the refueling vehicle. After all services are completed, the top left robot moves out the stair truck and they all go back to their depot locations. We also show that we can scale up our algorithm to 40 robots and introduce robustness measures.